Hello again, I'm George Flew and I'm the developer of the 3DUtility toolbox for 3D substation design. And in this video I will cover substation lightning protection design. Before starting, however, let's review the substation configuration. This is the same substation we've used in our previous videos, and we're coming into a 2-bay substation with 161 kV and stepped it down here to 12 kV where we've got 3 outgoing underground bays on this bank and 3 outgoing overhead bays on this bank. One of the most popular applications for designing lightning protection systems and substations is the rolling sphere method based on IEEE Standard 998. However, this method is going to be daunting for many designers, causing them to revert to add-on or standalone apps that require additional investment. This video will cover the graphic design of substation lightning protection using the equations for the rolling sphere method, but applied utilizing your vanilla AutoCAD and standard AutoCAD commands and simple AutoLisp routines. Again, in my demonstration, I'll be using BricsCAD. However, all commands that I'll be using are identical in AutoCAD, and all the apps will run without modification in AutoCAD. And now at this point I want to emphasize that this is a demonstration and not a training video, so I won't be going into detail on the CAD commands. Now IEEE Standard 998 is their guide for substation lightning shielding. We'll be looking particularly here at the rolling sphere model, which is one of the more popular models being used today. So let's just go directly to the diagram here that shows how to apply the rolling sphere. We're looking at a elevation of the substation, so we're looking at the sphere as a circle with the radius of the sphere as being S. And as explains here, as the sphere rolls along the ground, as it contacts a grounded metallic surface, in this case the fence, it will then swivel up until it either contacts or comes back to the ground. In this case we're contacting a structure, and at that point again it will swivel, and so it will create a number of arcs along this elevation view that would represent the surfaces that this sphere would create. And so everything that lies under this arc then would be protected. Just point out over here this breaker, which it says is unprotected, then I would take that to be a live tank breaker, since if it was a dead tank and grounded, that arc should come down and make contact here at this corner, and then as it swivels back down here to the earth, the contact point should be tangent to the diameter of this circle. Now from 998 we get a number of equations which I have summarized here in this spreadsheet. So the first thing we're looking for here is the sphere radius here, S, which is calculated from this equation, which is 8 times K. K is this value here, which recognizes whether it's a static wire or just a lightning mast, times the surge current raised to the 0.65. Now the surge current up here comes from this equation, which is the BIL, and the BIL, for instance, 161 kV is 750 kV. For 15 kV, it's typically 110 kV. So it's BIL times 2.2 divided by the surge impedance. The surge impedance then is given by this equation, which involves two values: the height of the bus above the ground and the corona radius. And then R sub C is given by this equation here, which is a rather complicated equation because R sub C is a function of itself. So the corona radius then, to solve for that, we need to use an iterative technique that solves this equation for 0, and I have used the what if analysis. We want to take this cell and drive it to 0. So under the what if analysis, the goal seek, we want to take cell C6, drive it to the value 0 based on changes to the cell to the RC value, which is cell C2, and so OK, and then you see this value gets driven close to 0, 7 times 10 to the minus 5. that certainly is close enough to affect this in maybe the 5th or 6th decimal place. So that's the solution here for 110 kV. Now let's start out and let's actually go to 161 kV. If we go over here to our bus and we just do an ID and tell it we want to hit near to this 161 kV bus. This is the tallest bus in the group. It says it's 27 feet and 6.5 inches off the ground, and that's a 4-inch bus. We went to the center of the bus, so add another couple of inches, be 27 feet 8.5. Let's just call it 27 3/4 feet. So if we go back here, and we've already got the 27 3/4 plugged in. If we put in our 750 kV BIL for 161, then this number doesn't seem to be updating as it should. We'll just go ahead and recalculate it. And there you see we've driven it down to 0.0003. And so this is our R sub C. And let's come down here. Let's change this to 1. And so for a static wire, we have a radius of our sphere is 74.9 feet. Now, at 110 kV, we actually run into a limitation. According to IEEE 998, they suggest that you limit this number to 2 or 3 Ka. And here I've limited to 3, so any value below about 69 kV will give us a maximum of 3, a minimum of 3 Ka, which says that we have a 99.55% chance of it being 3 Ka or greater. So that's what we're looking for. This is a minimum value. So we have a 0.45 chance of it being less than this and actually running into a problem. And you'll see that if we change this to 69 kV, which I believe is 350, it's not above this number. If we go up to 450, which is would be 115 kV, then we begin to see some changes here. But let's go back down to 110 kV, which would be our 15 kV. And so at that point we get a radius for our sphere for an overhead ground wire of 53.6 feet. And if we go ahead and calculate it for a tower or a mast, we get 64.3 feet. So I'm going to take then this spreadsheet and push it over here to the other screen where I can refer to it when I need to, and we don't have to keep flipping back and forth. Okay, so now we're ready to jump in our design. First thing I want to do here is I want to turn on this layer that'll give me some layout lines. So our first approach to this is to lay a static wire directly over the center line of our transformer. So if we move down here, let's open up our toolbox here, and we're going to go up here and filter under our structures LM for lightning mast. And you notice here we have 55 through 85 foot to choose from. In the fixed angle, we went for the 65, and it's a little counterintuitive that you might go for the 55. But if we go back here to our spreadsheet, you'll see that the radius for the overhead ground wire is only 53.5 feet. So if we go above that, we actually will lose some coverage. We'll see that here in just a minute. So let's go ahead and insert our lightning mast here at this intersection point. And then we won't need that anymore. Then on the other side, to run our mast to, as we did in the fixed angle, we'll just put a line here to represent our dead end pole. And we'll come in here, just set a line and go over here to our editor here, and we'll change that to a 64.5 foot pole or attachment point, and assuming that whatever our restraints were on our fixed angle, we'll stay with those here. So Now at this point, what we need to do is, as we looked on our rolling sphere, as the sphere comes up and contacts these, and we need an arc here to represent that surface that we're going to create between these. You would think that AutoCAD would be good at drawing an arc that would start at a point and be tangent here to the ground line, but in fact it doesn't really like that. First off, though, we want to take and change our UCS in line with this view so that we're in the XY plane in drawing this arc. Arcs are one of those 2D things that have to be drawn in the XY plane. So I am going to then, since we can't use the arc command, I've got an AutoLisp app that I've put together, APTR, which stands for Arc, Point, Tangent, Radius. So I'm going to give it the arc command, and then I need to select a point, and I'm going to select the node point up here on this pole, which would be our initial connection point for our static wire. And then I need to give it a point that we want it to be tangent at the ground line, and then the radius of 53.6 feet. And there we have our arc. Now what I should have done first is gone down here. I've got some layers set up for our lightning protection, so I should have gone ahead and put that on that layer, and we'll just go back into our properties editor, and we'll move that up to the L1 layer. And so there we have our first arc, and then we want to go up here and do the same with our static pole. So we want APTR, and again we'll pick the top of the pole, pick the line, and it remembers the angle. Now you can see why I mentioned we should make this the height of the pole, what we did. So if we look back at this, and here you can see we're looking down the line from the static mast back to the drop-in pole, and you can see if I select this arc, you can see that our center of our arc is actually below the top of the pole. So if you can picture this sphere rolling toward this static here, you can see that the sphere will actually have to roll underneath the static before it intersects with that static line here. So on the other hand, if you look down here at the one on this one, because it's only just a little over a foot, it's not even a foot above it, then that effect is negligible. So you can see we're going to lose a little bit of our coverage as we roll back. It's not going to be significant, but it is something you want to keep in mind. So let's go back here, and what we want to do at this point is we will need to create now our surface between these two arcs, and the command to do that in AutoCAD and BricsCAD is loft, and it will generate a surface between any two boundaries, any two appropriate boundaries. I better be careful about that. And so you can see here that we have our surface that comes in, and as you look at this, you see that we have this part of the bus that's inside the radius, and so it is not covered. So looking at that from overhead, we're going to take a similar approach that we did in our fixed angle, and that we're going to rotate this static. And let me just say, we can't go all the way to where we cover all of this bus. If we go too far, then our static pole, the distance between here and here will exceed the radius of our sphere, and the sphere will drop to the ground and will not be above our structure. So I'm going to pick, let me flip my UCS to the view, because if I'm going to rotate this, I have to be in the XY plane to do that. I'm going to select our surface. I'm going to tell it to rotate. Let me turn this off, and then I'm going to rotate it till I just cover this bus going out to the riser. That's going to leave this bus uncovered. we're gonna look at how we're gonna take care of that. So let's go back to the end on view, and again, as you can picture, as the sphere is rolling this way, when it encounters that bus, it will swivel up until it hits this static pole or the static wire up here. So we're going to generate another surface that will simulate that ball rolling and swiveling at the edge of this structure. And so, but to do that, I'm going to have to put a line up here along the top edge of this it simulates the static because I can't snap to this surface. So here's our line. There's a line up there that'll give me something to snap to here in a minute. So what we want to do then is, again, we need to have our be looking in on the XY plane. So here again, UCS view, so that we're in the XY plane. And then we go up here and we can create an arc. This time it's just a plain arc, and we can start here at the end of this at the corner of this structure, and we can tell it a radius of 53.6 feet. And then we come up here and we want it to be, we want to intersect here somewhere near, we want to hit the near point on that line. And again, we want to create then another arc so that we have two arcs first for our surface. Again, we want to start here at the end of at that corner, radius 53.6 feet. I don't know that I understand why AutoCAD doesn't remember the radius of an arc like they do for a circle. And then again, we want to intersect it near to this line here, so we'll get right there. Now we have our two new arcs, and so we want to again use our loft command. We want to loft from the last arc to this one, and now you see that we have we have increased our coverage to the point, and all we lack, as I pointed out a while ago, is on the end of these, because you have your surface that obviously ducks underneath these to get to that point. Here's my solution to that. You might find another one. I'm gonna construct a line, because I don't have a place to actually put it at this point. I'm going to start as a midpoint on this where this member hits this top of this T member. So I'm going to hit midpoint there. You'll see why in just a minute. I'm going to draw a line up, and then as I've done before, I'll go in here to the properties. I'm going to pick a 20-foot length on that, and you'll see why here in just a minute. And then the last thing I want to do is I want to move this line over. I want it to be right in the center of this column, which means I need to move it over 6 inches. So I'm going to move that line. It's in the x-axis, so minus 6 inches, comma 0. And now we're right in the middle of this column, as you can see here. And what I'm doing here then is I'm going to use this as a lightning mast. So so as a mast, we want to come back here. I need to, okay, wanted to make sure we've got the correct UCS. So what we need here is we need to go back to the APTR command, and we want to pick up the end of this. And again, we want to come down to this same ground line that we had hit earlier, and with a radius of this time we want to use our mast radius of 64.3 feet. And so we have a new arc here, and where we use the loft command to go between two arcs. What I want to do is create something that will look here like a tuba horn on this. So I am going to take this and use the command, the 3D command revolve. Again, this is both AutoCAD and BricsCAD. I'm going to tell it to revolve that, similar to similar to the mirror command, I've got to give it an axis to revolve around, and by default 360-degree revolution. And now you see that we have complete coverage of this, of the 12 kV portion of this. Now we still got a little 161 sticking out. We actually wound up covering this part of the bus. Something I need to do, I should have done a while ago before I did all this, is let me just do a quick move. I'm gonna move this this static mast up, and I'm gonna just kind of eyeball it, because what I want to do after that is just grab this. I need to get up here where I can select it, and I'm just gonna grab it and just move it up here to that node, and so I've got it connected up correctly there. And okay, so then at this point, I'm going to take all of these surfaces and do a mirror. Not yet. I am. Let me UCS view, because I need the mirror. I need to be in the XY plane. So I'm going to take all of these surfaces. I hope I selected that, and I'm going to mirror, and mirror it along this center line. Over to here and hit enter, and so now I've got both sides of the station done. At this point, that what's left is everything in the middle. Well, let me go back up here. When I mirrored that, I didn't mirror the static pole, so let's do mirror again. Let me pick the static pole. I don't know why I leave that out every time. Okay, so now we've got the static pole. So at this point, what we want to do is go in and create a surface to cover this. And let's go back again and look at our circle. So our rolling sphere. So as it rolls up over the top of this static, comes over and rolls over the top, then there's an arc between the two static wires. And that's what I say, you got to be careful if you spread these too far, so that arc is greater than the radius of the sphere. You can have that sphere just drop down on the ground and miss and not cover any of this. So at this point, we're going to again before we do that, I need to make sure I'm in the right UCS. So UCS view. You've got to be very familiar with this UCS if you're going to be doing this 3D. So I'm going to draw an arc. I'm going to start at this node on this pole. This is why I moved the static pole. I'm going to tell it radius, and this will be 53.6 feet because I'm going between two static wires. Come over here and pick the node on this pole. Now I've got an arc. If we just take a quick look, you can see it's well above all of this structure. And to complete that, so you need to come back and then put another arc between our two dead end poles. Radius 53.6 feet. And then we go to the other pole. Now we have two arcs here, and we can use our loft command. And we can loft between this arc and this arc. And now we can see our complete. Let me get rid of this extra, this arc here. We don't need that. You can see our complete substation coverage. Everything here is well under our rolling sphere for the 12 kV radius. And as you look from the top, everything is well covered. You could take my word that the switch is going to be covered, but we'll just go in here and do a change our layer down here to L3. Let's go ahead and turn that one off, and then we'll go back in here. We need to first come in here to the end and make sure our XY plane is set correctly, and so we'll do an arc point tangent radius, and we'll pick up again our node point here on the far side of the pole. We'll pick up this ground point here, and our radius for the 161 is 74.9 feet. So there is our arc for 74 for the 74.9 feet for the 161. We'll come back here and again use our APTR and 74.9, and then we will loft these two. Lost the last one and this one, and then if we look from on high, we are well over the top of our 161 switch with that one. I don't think we need to go any further with that. It's just the same thing over here. We'll do the same arc in here, but it'll have a bigger radius, so it'll actually will cover will be even higher above the substation than the 13 kV or 15 kV arc, so which already covers it. So there you go. We've got our complete coverage of this substation, and we didn't roll any spheres. As a matter of fact, what we used here was what I might term the lofting arc model, where we've used the equations from the rolling sphere to develop the radius of the sphere, and then used arcs to represent the contact points of our sphere, and then generated surfaces between those arcs to see what our coverage is. And so with that, that's going to end this demo. As always, you can, if you want to contact me, have any questions, any comments, you can go to my website, which is www.the3DUtility.com, and in the upper right hand corner there's a menu and a contact. If you have a question, be sure and include your email address so I can get back with you. And so with that, until we do another one, thank you.